integration. So today we want to look at finding the average value of a function. This is not in our maths tables, so I'm going to show you where this formula has been derived from. So you do not need to know this proof, this is more just out of interest where it has come from. So if I take the function and I mark in limits a and b, and then I take the area under the curve and I divide it into equal widths of interval delta x. So generally we use delta to represent small or tiny changes. Then often we call a x0 and b x of n. And therefore if I'm dividing these up into equal widths, the first one would be x1, x2, x3, and so on, all the way up until we get to the previous one before the last one, which would be x of n minus 1. So obviously there can be an infinite amount of these equal intervals underneath this curve. So I'm only showing a small scale of it. So therefore, if I'm looking at the width of each interval, delta x, well, what I can say for delta x is that if I look at this graph, then if I go from 0 to b, and then I go from 0 to a, and then I subtract it, I'm left with the difference between b and a. And if I've drawn n number of equal intervals, then the width would be the difference from b minus a divided by however many intervals I have drawn. In other words, I can say that n must be equal to b minus a divided by delta x. So in general, if we're getting the average value of y, in other words, our outputs of the function, well, what we would normally do is take all of those outputs, so whatever I put in for x, so in other words, if I've gone out x to a, I'd sub that into the function, and that would give me my, it would give me this height, this height, this height, and so on. Then my average would be the sum of all of these outputs divided by the total number. That's how we would normally find an average. But of course that could be quite tedious if we have a lot of these values. So we have just written down what n was, where we said that n, if I go back, could be written as b minus a over delta x. So therefore, if I'm dividing by a fraction, I would normally turn it upside down and multiply. So that would be the same as saying 1 over b minus a times the sum of all of those outputs times delta x. But if I increase the number of those intervals, in other words, as I get n tending to infinity, then what actually happens is we end up with the sum of all of these intervals being our summation of all these tiny parts, which is integration. So as n tends to infinity, our average value is actually 1 over b minus a of the integrand between the limits of b and a of our function, and delta x becomes dx. So this is not in our maths tables, and we need to know that off by heart. And remember that that symbol basically means summation of all of the infinitesimally small parts. In other words, as n tends to infinity. So if we go to page 416 in our book and we look at question 1 as our example, the first type here is where we're basically given a graph, a bit like in the proof, and we're asked to use the graph to estimate the average value between the interval of 1 and 3, and then complete the table and hence find another estimate for the average value on the interval of 1 and 3, and then use integration to find the average value on 1 and 3. And you'll see that obviously the more intervals we have, the closer we get to the true average value, which is obviously by integration. So let's complete the table. So our first bit is to write down our table for our input, our function, and our output, where y is equal to x squared plus 1. So what you'll do then is page 417, question 2. So type 2 is where we don't have any graph. We're just literally asked to find the average value of the function. So it's just straightforward. And we're given the interval of 0 to 3. So we literally just write down average value is going to equal 1 over b minus a between the limits of b and a for h of x dx. And again, the more you write down this formula as you're doing these questions, the more you're going to remember this one off by heart. So we're putting in our limits of b and a. So b must be the upper limit, which is 3, and a is the lower limit, which is 0. So that's 1 over 3 minus 0. Limits are 3, 0. Function is x to the power of 4 plus 2x squared dx. So that's 1 over 3. If I integrate x to the power of 4, I get x to the power of 5 over 5. If I integrate 2x squared, I get 2x cubed over 3. And then my limits are 3 and 0. So subbing in my limits, I get 1 over 3 times 3 to the power of 5 divided by 5 plus 2 times 3 cubed over 3. And then if I put in 0 there, I'm just going to end up with 0. So therefore that gives me 22 and a fifth. So you're going to do for me question 3. I have done part 3, so you're going to do part 1, part 2, and part 4. So just straightforward polynomials. And then you're going to do question 4, just to remind yourself and revise your sine, your square roots, your exponentials. So just do part 1, part 2, and part 3. Don't worry about integrating sec squared. So our third type then is the real world. So again, if we're looking at page 417 in your books, you'll see here the population of a certain region can be approximated by the population with respect to time, which is given by 145 e to the power of 0.1 t, where p is in thousands and t is the number of years since 2016. We have to find the average size of the population from 2017, and that should be to 2021. So if you just change that in your books. So again, what we're going to do is we're going to make sure we're stating that P is our population, and that's in thousands. T is our time, and that's the number of years since 2016. So therefore, we're looking for the change of time, which is 2017, 2021. So that means our interval is changing. Well, 2017 is 1 year since 2016, and 2021 is 5 years since 2016. So since the start of 2016 would be 5 years. So our average value then is found again by getting 1 over b minus a for the integrand of BA on our population, and we're integrating with respect to t. So b and a is our lower limit, b is our upper limit. So therefore our average value, and it's the average size of the population, is equal to 1 over 5 minus 1. Upper limit is 5, lower limit is 1, and we're integrating 145e to the power of 0.01t with respect to time. So remember, when you're integrating an exponential function, it is just itself divided by the derivative of its power. So that's 145e to the power of 0.01t. And if I divide by the derivative of the power, well, the derivative of 0.01t is just 0.01. And that's within the limits of 5 and 1. So therefore that's going to be 145e to the power of 0.01 times 5 divided by 0.01 minus 145e to the power of 0.01 times 1 over 0.01. So if I put all of that into my calculator, what that gives me with then is the average size of the population. It's approximately 149.426, and that's, remember, in thousands. And it didn't ask for any significant figures or anything like that, but let's just round this up. So our average population is approximately 149, which would be 149,426. Okay, so what you're going to do for me then is question 10. Yeah, I'll just leave it at question 10, okay? So that's the end of the chapter, which means then revision and then test next week.